Okay, so we saw hydrohalogenation of alkenes. We kind of walked through that in a lot of different steps. We started with the symmetrical one, then we talked about really like piece by piece, but we're going to jump right into the deep end on hydration of alkenes because it's basically the same situation, just not HCl, not HBr, not HI, so that's the hydrohalogenation. This time we have a different acid and we have a different kind of solvent that we're in. So it should be pretty similar though once you kind of walk through the steps mechanistically. So again, this is our nucleophile. Our pi bond is going to supply the electrons, so it is looking for a partial positive. Where's that partial positive going to be? The partial positive is going to be, in this case, if we think about our groups, we know that sulfuric acid is a really strong acid. We've seen that for a while, and if we think about the structure of sulfuric acid, we have essentially a big electron withdrawing group and an OH, so that's going to make a big partial positive there that would be a place for that pi bond to give its electrons to. So just as the HCl, the partially negative pi bond added to the partially positive hydrogen of HCl, HBr, the pi bond's going to give its negative electrons to that hydrogen there, and the OH bond is then going to break. So that would mean that we added a hydrogen to either that side or that side. Is there going to be a preference for side here? And in this case, the answer is no. It would be a secondary carbocation on that side, secondary carbocation on that side. So we're going to have hydrogen to one side, carbocation on the other side, and we would also form a roughly equivalent amount of the hydrogen on this side, the carbocation on that side. So at this point, the question becomes, what's going to now add to that positive charge? We have the conjugate base of sulfuric acid around. We have water around. Which of these is a stronger nucleophile? And remember, we would relate nucleophilicity to basicity, stronger base, stronger nucleophile. And the way that we could probably most easily say which one's the stronger nucleophile is look at the strength of the conjugate acid. So the conjugate acid of the sulfuric acid conjugate base is sulfuric acid. So we can say H2SO4 is that conjugate acid. Conjugate acid of H2O would be H3O plus. So what are the pKa's of these? The pK of H2SO4 is -3. The pK of H3O plus is -1.7. So if this is the stronger acid, that means this is the weaker base, weaker nucleophile. So this is the stronger nucleophile. H2O is a stronger nucleophile, a stronger base than this anion here. So the stronger nucleophile, stronger base is going to be what adds to our positive charge. OH2, if you think about it, has partial positives on each of those hydrogen atoms, a partial negative on the oxygen. It is a weak nucleophile, but if we have a full positive charge on something, just like we learned about in the substitution chapter, this partial negative is going to be attracted to it just the same. So the negative flows to the positive, and in that case, it's going to add to two different locations on the molecule, both that carbon and that carbon. Is it going to add to the top, the back, or both? Both, right? It's an empty p orbital, so it's just as empty on the top as it is on the back face. So that's going to mean we're making a mixture of, and actually, let's draw out. We're going to draw out the intermediate from this one here. So that would produce the OH2 plus, and then we're in water. There's a lot more water around than there is any of these molecules. So water can then, it's the stronger base around, can transfer a proton to itself, and that will produce the OH, the alcohol product. It's called the hydration because we technically added a hydrogen there and an OH, so we technically added H2O hydration. Hydrate comes from the word hydrate, which relates to water. So H2O is added. It can also add to the other position, right? We also added it to there. So we're going to make a mixture of that and that. And again, I didn't really need to draw in the hydrogen, so I'm going to remove those from the molecule. It's implied in the structure. But this is a 1,3 substituted cyclohexane, a 1,4 substituted cyclohexane. So those are very different products. What else? In the course packet in the middle, I wrote hydrohalogenation. That was a typo. Changed that out for hydration. Hydration makes both the syn and the anti-product, right? The H that's here could be on the same face as the OH, or it could be on the opposite face of that OH. So it makes a mixture of that syn and anti-addition product. And again, change that hydrohalogenation to hydration. That was a typo. Okay. Okay, the course packet now says, what if there's a strong acid, H2SO4, in the presence of an alcohol? So I think that you guys have enough right now to be able to predict this product without me saying anything else. So pause the video and give that a go. Okay, maybe you need a little bit of help. Well, we just saw sulfuric acid with water. So now we're just changing out water for CH3OH. What is the pKa of an alcohol? 16. What is the pKa of water? 15.7, so basically 16. So CH3OH is going to do pretty much the exact same thing the water's doing. It's the solvent. It's going to do the exact same thing as the water solvent does in the presence of the sulfuric acid. So now that you've heard that, you need a little bit extra help. Go ahead and predict the product. Okay, nice job. So what's happening here? Well, we have our strong acid and got our partial positive, partial minus. This pivon is going to be attracted to that. Are we going to add our hydrogen to this side or to this side? If we add the hydrogen to this side, that means we're going to have a secondary carbocation. If we add the hydrogen to this side, we'd have a primary carbocation. We want the more stable carbocation. So that means we're going to add the hydrogen here and have the secondary carbocation here. Secondary carbocation there. So what's the next step going to be? Well, the water or the methanol could add to that position, but is there anything else that can happen first? Yeah, we have a secondary position right next to a tertiary position. So a 1,2 hydride shift would very nicely change our secondary carbocation to a tertiary carbocation, which again, the tertiary carbocation is the more stable carbocation, so that's obviously going to be an intramolecular transfer that is favored. At this point, our methanol can then add to that position. That would add both to the top and the bottom. Do we have to draw the wavy thing here? No, again, this is an achiral molecule. So we can just draw OH and a CH3, positive charge, and then we have lots more of those around. So that's going to transfer a proton there, and the final product will be that ether product. So that is how that one works out. It should be very similar. It looks identical to if this is water. If this was water instead of CH3OH, it would just be OH, but the mechanism works exactly the same. So you should really be trying to understand mechanisms, not memorize reagents. Yeah, keep up the good work.